Hello students, welcome to ICSE, CBSE and WBBSE solution by Prudence Coaching.
This is the class 3 of your chapter real number, and today we are going to start with part 2. In the part 2, we will deal with the fundamental theorem of arithmetic, which we also call prime factorization method. Let us understand this theorem in details. By this theorem, it means every composite number. Do you know what is the meaning of composite number? A composite number is a positive integer that has at least one divisor other than 1 and itself. For example, 5. 5 is a prime number. Why prime number? Because we can divide 5 by 1 and the number 5 only. But in case of 4, we can divide 4 by 4, 1 and also we can divide it by 2. Therefore, it has a factor or divisor other than 1 and 4. So, it is a composite number. Every composite number can be expressed or factorized as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. That means the occurrence of prime factor may be same as we are arranging it in ascending order, but you must remember that the factorization is unique. No two number will have same factorization. Let us look into the proof that the prime factorization of a natural number is unique. Unique means it's one of its kind, except for order of its factors. Order of its factor can be same, but the prime factorization is different. In general, given a composite number x, let a composite number be x, we factorize it as x equals to p1, p2 until pn, where p1, p2 until pn, all these numbers which are prime numbers are written in ascending order. That is, p1 is smaller than p2 and similarly it goes on. And by combining the same primes, we will get powers of primes. For example, the prime factorization of the number 32,760 is 2 into 2 into 2 into 3 into 3 into 5 into 7 into 13. Now, as you can see, the prime numbers are arranged in ascending order and the number of 2 here is 3. So, we have written 2 to the power 3 and the number of 3 here is 2. So, we have written 3 to the power 2. The number of 5, 7 and 13 is 1. So, we need not to write 5 to the power 1, 7 to the power 1, 13 to the power 1. We can simply write it as 5, 7 and 13. So, our final prime factorization of the number 32,760 is 2 to the power 3 into 3 to the power 2 into 5 into 7 into 13. Students, now it is clear to us that the prime factorization of a natural number is unique except for the order of its factor. Let's see some of the examples before starting with the exercise. Let's go through the example number 5 from your NCERT mathematics book. Consider the number 4 to the power n where n is a natural number. Check whether there is any value of n for which 4 to the power n ends with the digit 0. So we need to check here that is there any possible values of n where n is a natural number such that 4 to the power n ends with the digit 0. As here we need to find out whether the number ends with a 0 or not. Before this, we should know that to end with a 0, it should have a multiple of 10 in it. So, it must have a 5 and a 2 in it. As we know, 5 into 2 is 10. So, if 4 to the power n is a number which ends with a 0, then it must be a multiple of 5 and 2. Or you can say that there must be prime numbers 5 and 2 in it.
Let's see the solution. If the number 4 to the power n for any n were to end with the digit 0, then it would be divisible by 5. That is, the prime factorization of 4 to the power n would contain the prime 5. This is not possible because 4 to the power n equals to 2 to the power 2n. So, the only prime factorization of 4 to the power n is 2. Also, you can write the uniqueness of fundamental theorem of arithmetic guarantees that there are no other prime in the factorization of 4 to the power n. So, there is no natural number n for which 4 to the power n ends with the digit 0. So, let's start with the next example.
Now, let us go through the example number 6. Find the LCM, lowest common multiple, and ACF, highest common factor of 6 and 20 by the prime factorization method. In order to find out the prime factors of a given number, we need to divide the number by the prime numbers which are smaller than the given number and check whether the prime numbers divides the given number completely without leaving any remainder. If the prime numbers divides the given number without leaving any remainder, then the numbers or the prime numbers are the factors of the given number. We need to remember one thing: when we are checking whether a prime number divides the given number completely or not, we need to start with the smallest prime number, or we need to move in ascending order. If we divide 6 by the smallest prime number, that is 2, then we will get a quotient, that is 3. Now, if we divide 3 by 2, we will see that 3 is not completely divisible by 2, as we will get a remainder 1 in case we divide it by 2. So we need to check it whether it is divisible by 3 or not, which is the next prime number. 3 is divisible by 3, so as a result we will get a quotient 1. Whenever our quotient is 1, we need to stop in that case only, and we will get our prime factorization, that is 2 into 3 into 1, or if we arrange it in ascending order, then it will be 1 into 2 into 3. Similarly, when we check the prime factors of 20, first we need to divide it by 2, as it is completely divisible by 2, and as a result we will get a quotient, that is 10. Now, we will check whether 10 is divisible by 2 or not. Yes, 10 is divisible by 2. As a result, we will get a quotient 5. Now, we need to check whether the quotient is divisible by 2 or not. No, it is not divisible by 2. So, we will check whether it is divisible by the next prime number 3 or not. No, it is not completely divisible by 3 also. So, we need to check whether it is divisible by the next prime number, that is 5. Yes, 5 is divisible by 5. As a result, we will get a quotient 1. Whenever we will get a quotient 1, we can write the prime factors of the given number. So here the prime factors of a given number is 1 into 2 to the power 2, as we have two 2's here, and into 5. Now let us see the solution. We have 6 equals to 2 to the power 1 into 3, and 20 equals to 2 into 2 into 5, that is 2 to the power 2 into 5. You can find the ACF of 6 and 20. ACF means highest common factor, the highest number which can divide 6 and 20 without leaving any remainder. As you can see, the highest common, that is the maximum common number which we have within 6 and 20 is 2, and we don't have any other common number between 6 and 20. Therefore, the highest common factor is 2 here. Now, the LCM of 6 and 20, LCM is the lowest common multiple. That means LCM will be the lowest number which can be divided by 6 and 20 without leaving any remainder. In order to divide the LCM by 6 and 20 without leaving any remainder, we need the highest powers of the prime numbers. Here the highest power of 2 is 2 to the power 2. So we have written 2 to the power 2, and the highest power of next prime number, that is 3, is 1. So we have written 3, and we have another highest power of 5, that is 5 to the power 1. So we have written 5. As a result, the LCM of the number is 60. So like this, you can find the ACF and LCM as you have learned in the previous classes. Now if you note, the ACF of 6 and 20 is 2 to the power 1, which is the smallest power of each common prime factors in the number. Students, the common prime factors or the common prime in the given numbers, that is 6 and 20, is 2, and the smallest power is 1. So 2 to the power 1 is the ACF. LCM of 6 and 20 is 2 to the power 2, 3 to the power 1 into 5 to the power 1. That is the product of the greatest power of each prime factor involved in the numbers. In the two numbers, that is 6 and 20, we need to take each and every prime number with its greatest power. Here we can see the smallest prime number is 2, and the power which is greatest is 2 to the power 2. So we have written 2 to the power 2. Next prime number is 3, and we have greatest power of 3, 1 in both 6 and 20. So we have written 3 to the power 1. Next we have 5, and the greatest power of 5 here is 1. So we have written 5 to the power 1. In such way, we have found out the LCM, that is 60. From the above example, you might have noticed that the ACF of 6 and 20, that is 2, into LCM of 6 and 20, that is 20. That is 2 into 60 is 120, equals to 6 into 20. That is the product of the given numbers. In fact, we can verify for any two positive integer a and b, ACF of a and b into LCM of a and b equals to a into b. We can use this result to find the LCM of two positive integers if we have already found the ACF of the two positive integers. So let's see the next example.
Example number 7 is find the ACF of 96 and 404 by prime factorization method. Hence, find their LCM. First we need to find the ACF of 96 and 404, and we need to use the value that is ACF to find their LCM. So let's start.
Solution. The prime factorization of 96 and 404 gives 96 equals to 2 to the power 5 into 3 and 404 equals to 2 to the power 2 into 101. Therefore, the ACF of these two integers, that is 96 and 404, is 2 to the power 2, that is 4. Because as we can see, there is only one common prime between 96 and 404, that is 2, and the smallest power of 2 here is 2. Therefore, 2 to the power 2, that is 4, is the highest common factor of 96 and 406. That means 4 is the highest number that can divide 96 and 404 without leaving any remainder. Now, as we have found out the ACF, that is 4, and we know that LCM of the given numbers into ACF of the given numbers equals to product of the numbers. So we can write LCM of 96 and 404 equals to 96 into 404 divided by ACF of 96 into 404. Therefore, the LCM of the given numbers, that is 96 and 404, is 9696, that is 9696. Let's see the next example, that is example number 8.
Example number 8 is find the ACF and LCM of 72, 6 and 120 using the prime factorization method. Solution. We have 6 equals to 2 into 3, 72 equals to 2 to the power 3 into 3 to the power 2, 120 equals to 2 to the power 3 into 3 into 5. Here 2 to the power 1 and 3 to the power 1 are the smallest powers of the common factors 2 and 3. As you can see, within 6, 72 and 120, the common factors are 2 and 3. And the smallest power of this common factor, if you see, the smallest power of 2 is 1 here, and the smallest power of 3 is also 1. Therefore, the ACF of 6, 72 and 120 is 2 into 3, that is 6. So 6 is the highest common factor or the biggest number which can divide 6, 72 and 120 without leaving any remainder. So 2 to the power 3, 3 to the power 2 and 5 to the power 1 are the greatest power of prime factors 2, 3 and 5 respectively in the three numbers. Therefore, the LCM of 6, 72 and 120 is 2 to the power 3 into 3 to the power 2 into 5, that is 360. Because as you can see here, the prime numbers are 2, 3 and 5. And the highest power of 2 here is 3 and the highest power of 3 is 2. In case of 5, the highest power is 5. Therefore, the LCM is 360. That means 360 is the number which can be divided by 6, 72 and 120 without leaving any remainder. And you must remember that 360 is the smallest number which can be divided by 6, 72 and 120 without leaving any remainder. So we have found here that the ACF of 6, 72 and 120 is 6 and LCM of 6, 72 and 120 is 360.
Students, we will start with exercise 1.2 in the next class from your book. Till then, keep practicing, keep improving. Thank you, students.